Section 2.1 sets. So we're starting a new chapter here, and I'm sorry, this first section is just a wall of definitions. Take the time, read back through these even after I go over them. I'm going to try in my lecture to really emphasize the details that might get lost. So let's dive right in. A set is an unordered collection of objects called elements or members of the set. So we're kind of generalizing some of the stuff and providing definitions and terms that apply to these structures you've been using for a long time in your math classes. And so one of the things you'll notice right off the bat is that we're talking about elements now. So we'll see some examples. They can be things like letters. That's a really common one to go to. So we're not just talking about numbers anymore. A set is said to contain its elements. Little a is the symbol in big A denotes A as an element of big A. I've already snuck this into some of our previous proofs, and I've been saying, hey, this K1 is a member of this set. Whereas the slice through the symbol says it's not an element that is a member of A. One common way to describe a set is to use the roster method, and this is the most straightforward. Just list off what's in it. So the set E of even positive integers less than 10, you could also just say, why didn't you just say 2, 4, 6, and 8? You notice one thing right off the bat here, we use curly brackets to denote that we're talking about a set and a capital letter. We separate our elements with commas. So in this case, there are 4 members and they are numbers. We could also say the set of positive integers less than 100 can be denoted. And this is still technically the roster method, even though we don't list them out. We do 1, 2, 3. Usually you need at least 3 or 4 elements to set the pattern, but here it's understood that you could fill this in with the rest of the numbers, right? We understand this to be all the numbers, or all the integers 1 through 99. The set builder method describes a set by stating the properties that the members have to satisfy. So here's how this gets written down. E is equal to, you'll see these curly brackets again, defining the set. So it's made up of members X, and then we have this vertical bar, and that's where you're going to list the criteria. So we're calling the elements X, and now I'm going to tell you what criteria they have to satisfy. X is an even positive integer less than 10, or you could say X are members of the positive integers, X is even, and X is less than 10. All of these E's on this page are defining the same set. We have some special sets. You've already been using some of these. When we use n, we use it to represent the set of natural numbers. One thing to note is that this can be different depending on the book you're using. In our book and for our class, we'll be using 0 to be included in the set of natural numbers. Z is the set of all integers. You've been using that one. Z plus is the set of positive integers. We've also been using Z minus. If you want to talk about the negative integers, Q is the set of rational numbers, and you'll see it being given there. P over Q, here's the criteria. P's got to be an integer. Q's got to be an integer. Q cannot be 0, right? So these are your fractions, integer over integer, where you can't divide by 0. R is the set of real numbers. R plus the set of real positive numbers, and C is the complex numbers. Two sets are going to be equal. That is, A will equal B if they have the same elements. So for example, these two sets are the same. The order does not matter. They all have elements 1, 3, and 7. These two are not the same because while they both contain 1, 3, and 7, the one on the left has 9, the one on the right does not. So they have to be exactly the same. The empty set is denoted this 0 with a slash through it. So you may have seen this in some of your other courses. This is technically what it means. So you should only be using this symbol if you're talking about a set. Some people do write their zeros that way, but for us, just to make it clear, that's going to be a set we're talking about, the empty set. So you also see the other way to represent it is brackets with nothing in it. That is different than containing a zero, right? Empty means we're a set with nothing in it. You could have a set with just the zero in it, in which case you have an element in your set. You're probably all familiar with Venn diagrams. We're going to be using them to visually represent some of the things that we see in this section. So if we go with this example, e is a set of positive integers less than 10. We could have our universe. In this case, I've just designed this problem to have the universe of all integers. E then would be represented by, okay, let's go ahead and circle up and label it with an E, 2, 4, 6, and 8. Right. However, typically in our Venn diagrams, however, you won't see the numbers. We'll just leave it to be understood that E is some of these elements. What do we need to describe that E? Well, E is a subset. If every element of the set A is also an element of the set B, then A is a subset of B, denoted with that symbol that you see there. This is where the details can be excruciating in their exactness. You notice that this means that every set is a subset of itself. And that's very counterintuitive. In fact, you'll see that down there in C as one of the theorems. We'll cover that in a second. That's not what people mean most of the time when they say subset, right? Just in conversation. What they typically try to mean, even though they don't say it, what doesn't come to mind, is a proper subset. That is, every element of A is also an element of B, and A is not equal to B. So if we let A be the set of citrus fruits and B be the set of all fruits, we can say all of the following. A is a subset of B. A, in fact, is a proper subset of B because, well, let me back up. A is a subset of B because all citrus fruits are fruits. A is not a proper subset of B because there exist some fruits that are not citrus fruits, thus A is not equal to B. And using the same logic, then, we can conclude that B is not a subset of A. There are fruits that are not in the subset citrus fruits. So we get two theorems here. I've already alluded to one of them that are not a... Once you get the definition, they make perfect sense. But in conversation, like if you hadn't seen this slide, these two thoughts may not have occurred to you. The first is that the empty set is always a subset. You can always take no elements as your choice. The next is that every set is a subset of itself. Not a proper subset, a subset. The cardinality of the set S is the number of distinct elements in S. If S is finite, we can write S kind of trapped in these bars. These kind of like it looks like the absolute value symbol, but contextually we know we're talking about sets. The absolute value of a set doesn't make any sense, so we're talking about the cardinality. So if it's a finite, we can draw the symbol and we say it's finite. Otherwise, we can't use that symbol. We just have to actually write out S is an infinite set. So if S is the set of letters in the English alphabet, the cardinality of the set S is 26. That is a finite set. However, if S is a set of positive integers, we just have to conclude S is an infinite set. Okay, so buckle up for just a second here. The power set of a set S, denoted with this fancy P of S, the power set, is the set of all subsets of S. So what about the power set of A, B, C? This is where understanding what an element is can be really helpful. We saw an example previously where elements were fruits, and then elements were letters, and elements were numbers. Since the power set is the set of all subsets, you'll notice that the element here is a set. The connection for you programmers out there is that this is an array, right? And we could store, integers in that array or letters in the array spots, but this is an array of arrays, right? So the elements are sets. We apply our theorem, and we note that right off the bat, one potential choice for the power set is the empty set. We get 3 individual sets. That is a set that contains only A, the set that contains only B, the set that contains only C. Then we get our sets that contain 2 elements, the AB set, the AC set, and the BC set. And finally, S. So one fact that then follows from this is that if the cardinality of the set is S, so if it's a finite set, the power set will have cardinality 2 to the n. And that's because every element, A, B, or C, either is or is not in each of the sets. So for the example we just saw, there are 3 elements, A, B, C. So 2 to the third is 8, and you'll see there was indeed 8 elements, 8 subsets that we could create from the set of S. The Cartesian product. Again, getting back to terms you may have heard of before, but we're redefining them right from the ground up. The ordered n-tuple is the ordered collection that has elements A1 as the first element, A2 as the second, and AN as its nth element. So the order here does matter. So 2 ordered n-tuples are equal if and only if each element is exactly the same in that order. The Cartesian product, of which you're familiar with at least one Cartesian product, you think of it as the Cartesian plane, of sets A and B are denoted A cross B, is the set of ordered pairs A comma B, where A, little a, is a element from the set big A, the set A, and B is an element from the set B. So there it is in the set builder notation. It's all elements A comma B. So the elements now are pairs, at least for this Cartesian product of 2 sets. For example, if we let A be the set AB and B be the set 1, 2, 3, then the Cartesian product A cross B is the set of ordered pairs A comma 1. So notice each ordered pair is now in parentheses, and it's always an element of A in the first position and an element of B in the second position. So if you let A be the set AB and B be the set of numbers 1, 2, 3, the Cartesian product has in it these ordered pairs. Oh no.